Welcome to The Explainer. Today, we're diving into a topic that quite literally surrounds us all day, every day. We're talking about the physics happening right inside the walls of your own home. We're going to unlock the math behind how heat actually travels through materials, zoning in on a specific area of physics known as steady state one-dimensional conduction. Now, I want you to think about a highly relatable and, let's be honest, sometimes really painful scenario: battling those sky-high heating and cooling bills during extreme summer or winter weather. It really forces us to ask an important question. How can we mathematically control the temperature of our environments? Because our goal today isn't just to stare at abstract physics. We want to see how we can use actual math to optimize building design and keep our energy exactly where we want it. So, here's our roadmap for this explainer. First up, we'll tackle the physics of heat flow and then introduce the thermal resistance analogy. From there, we'll look at building better walls, wrapping cylinders and pipes, and finally, we'll wrap up with a really mind-bending concept: the insulation paradox. All right, let's jump straight into Section 1, the physics of heat flow, specifically looking at one-dimensional steady-state conduction. So, one-dimensional steady-state conduction happens when temperature is a function of only a single space coordinate. But to really grasp this, I want you to compare Fourier's law of heat conduction to Ohm's law for electric circuits. Notice how absolutely identical they are? The temperature difference is the driving potential for heat, exactly like voltage is the driving potential for electricity. It's kind of wild, but heat flowing through a wall is mathematically identical to electricity flowing through a wire. Moving right along to Section 2, the thermal resistance analogy, and how materials act as hurdles to heat flow. If heat acts just like electricity, then it makes perfect sense that building materials must act as hurdles, or, resistors. Take a composite wall made of 3 different materials layered together. Just like adding electrical resistors in a series circuit, every single layer offers a very specific resistance to heat flow. And that's based entirely on its thickness and its unique thermal conductivity. Now, zooming in on that wall's cross-section, you can clearly track the temperature gradient. You've got this line stepping down as it passes through layers A, B, and C. And because the heat flow has to be exactly the same through all sections of the wall, the total thermal resistance is simply the sum of the individual resistances of each layer. Honestly, this analogy makes complex, multi-layered thermodynamics surprisingly intuitive. Okay, let's take this from theory to practice in Section 3, building better walls. Let's see how this translates into practical engineering. The absolute crucial bridge between textbook physics and the terminology you'd actually see walking down the aisle at a hardware store is the R value. In the building industry, R value classifies insulation performance. It is literally defined as the thermal resistance per unit area. So when you're out there buying insulation, you are quite literally buying a specific mathematical resistance to heat flow. Let's contrast some real-world examples straight from our source data using U values. U values represent the overall heat transfer coefficient. Basically, if R value is resistance, U value is the exact inverse, how easily heat passes through. So lower is definitely better. A standard 2x4 wood stud wall with absolutely no insulation in the cavity has a U value of 1.85. But look at what happens next. Fill that exact same cavity with polyurethane foam, and the U value plummets to 0.228. Meanwhile, an 8-inch solid normal weight concrete wall has a massive U value of 4.34. These material choices drastically alter a wall's overall heat transfer. But why does this actually matter to you and me? Well, think about this specific number from our source examples: $86.94. Based on a calculation comparing wall constructions for a small building in Texas on a blazing hot summer day, this is the actual monthly cooling savings achieved just by upgrading from an uninsulated wall to one with 260 millimeters of fiberglass insulation. Over $86 a month saved simply by using math to increase thermal resistance. That brings us to Section 4, wrapping cylinders and pipes and tackling radial heat flow math. As we all know, the built environment isn't just made up of flat walls. We have to account for curved geometries, things like plumbing lines and industrial piping. With a flat composite wall, the cross-sectional area that the heat flows through remains completely constant. But with a cylindrical pipe, as heat moves radially outward from the inside to the outside, the area is constantly expanding. Every layer further out literally has a larger circumference. Because that area is constantly expanding, the thermal resistance formula has to adapt. Now, without getting bogged down in doing the actual calculations right now, it's the conceptual shift that really matters. The math for radial heat flow is driven by natural logarithms. It requires you to know both the inside and outside radius values of the cylinder because it has to account for that increasing surface area. In a cylinder, moving outward means encountering more and more area. And that perfectly sets up Section 5, the insulation paradox, where more is sometimes actually less. Keep that constantly increasing area in mind because it leads us straight into a fascinating plot twist. Can adding insulation actually increase heat loss? Up until now, the rule has been pretty simple, right? Add material, add resistance, and you drop the heat transfer. But nature has a really fascinating exception when we're dealing with cylinders. The answer lies in a completely counterintuitive concept called the critical radius of insulation. This is a specific outer radius where heat transfer is actually at its absolute maximum. If your pipe's outer radius is below this critical value, adding insulation will actually increase your heat loss. No way, right? How is that even possible? Well, it's because on very small pipes, adding insulation makes the outer circumference much, much larger. That added surface area ends up dissipating heat into the surrounding air faster than the insulating material itself can trap it. Let's walk through a literal case study from the source material to prove this. Imagine a small 5-centimeter diameter pipe carrying 200-degree heat. If we wrap it in 3.17 centimeters of asbestos insulation, we naturally assume we're saving energy. But here's the kicker. Because the new overall radius is still smaller than the critical radius for that specific material and environment, we accidentally increase the heat loss by 25%. The increased surface area drastically outpaces the added thermal resistance. From trading heat like an electrical circuit to massive real-world cooling savings, all the way to the paradox of pipes that lose more heat the more you insulate them, the math of steady state conduction is just incredibly powerful. So, I'll leave you with this. How will you reconsider the hidden engineering of the environments around you? The next time you walk past a layered wall or a wrapped pipe, I really hope you see the physics at work. Thank you so much for exploring this with me on today's Explainer.